You're most welcome to this presentation by me, Obudra Ceasar, from University, Uganda, presenting this paper, Deep Reinforcement Learning Based Multi-Objective 3D Path Planning for Vehicles, written by Shuqiao Huang, XiruWu, and Guoming Huang. So this problem is simply just presented as if this is an autonomous vehicle which should find which route will be able to, let's say this is the target location, which route will it take? Should it move uphill and then it counts from there, or it should go from here the other side and then reach there, or it should move from down here and then maybe like that, or it should do from here go this way and be able to reach there. So this is the kind of problem we are trying to solve. Yeah, otherwise the presentation outline is it shall begin by introduction to the introduction, after which is about preliminaries of algorithms and mathematics. The third one is method, in which the structure of the DPN or the deep reinforcement learning it will be described. Design of the reward function, imitation learning using heuristic method, the experiments, and also the results. We will be dealing with the hyperparameters and their values, the reward during the training, the simulated path results for the 3DM and the DRL, where we are comparing the two, and then after that we shall get the results of the method, the 3DM, and then the DRL, comparing their energy consumption and distance covered to find out which one perform better, which we shall be able to draw conclusion, then look at the future works, and then the references to the outline. Otherwise, in the vehicle industry, there is a very big need to improve energy efficiency through research and development. Vehicles like that are in use in mining, exploratory robots, and space probes all face a very complex environment like the one I described before. Otherwise, to improve that, normal three aspects are focused on: that is battery management technology, optimal control methods, and the planning with the conservation of energy and distance, which is actually what we are looking at. So in this area, several works have already been published, like the 3DM method and other reinforcement learning methods. But also 3D reinforcement learning has been shown to potentially, solve very complex programming problems, path planning on 2D, and then also it can solve NP-hard problems like the PSP. So we want to see, can DRL solve this problem, where instead of just having 2D, we are jumping to 3 dimensions, and also the objectives are actually many, in this case two, in which we are going to trade off between distance and energy consumption. When a vehicle actually goes uphill, it may cover some distance, but energy consumption will be high. But also when it goes slope, I mean it goes up slope, but in a less up slope, the distance may be long, but energy may be consumed. We don't know. We don't know what we are supposed to do. The system to be able to make a decision to optimize, in this case, the energy. Yeah, so in this case, the preliminary is the 3D map which is used is the digital elevation map, where the z-axis denotes actually the altitude, the xy plane is the horizontal plane, and the then is assuming that each sampling pixel xyz can actually, be reached in the planning process. And also the concept of neighbor point is used, where the p lower n is the current point, and the p lower n plus 1 is the neighbor point nearest here, and the d is the distance from point to point is calculated using the 3D Euclidean distance, and the energy consumption between the 2 points is calculated using this equation 1. And this and the terms here, like the terms US and GS, which are actually the estimated energy consumption, either upstream or downstream, can be calculated using this equation. So also the this term and that term actually shows the upstream and downstream estimated energy consumption per meter, where the beta is given to be 30 degrees Celsius, and the units of these two terms is said to be used for this particular paper, and you can consider the beta from the upturn of these terms, where this term and that term are actually the coordinates of the two reference points where P lower n and P lower n plus 1 are found. And this term and that term are actually set at 25 U per meter per then. And based on this model, the energy consumption of the park is calculated using this equation. E total, the total energy consumption is equal to the sum of I from 1 up to b minus 1 of this total energy that has been spent. So how do we build the structure of the Qn? We can use this diagram to simplify this explanation. So our DPN is built using just three layers of parts. The first one is the input layer, whereby the input layer, and then it's followed by the convolutional backbone, after which is the fully connected layer. Now, when we look at the input layer, it is having we have transformed the input in the input from 100 by 100 by 3 into 50 by 53 to solve the difficulty in conversion of a PPN model down 50 by 50 by 3. And the convolutional backbone, which is the middle one, has two layers. These two layers plus two mass pooling layers. The first one is the first layer has 8 by 8 into 3 by 3 by 3, and the second layer has 16 into 3 by 3 by 8. Otherwise, for the max pooling, we went ahead and actually replaced the current target and the current and the target points using two rectangles, which actually makes the max pooling feasible, because it will be able to decrease the size of the filter map. If it was not done, the network volume will be very big, but also it can actually directly erase the important value, the important points, or you can say also that the CCNN keeps a big amount of the trainable parameters within it, and which will not be available for training. That makes training very difficult. But going to the last point of the fully connected layers, you will also be able to see that for it is also made up of three layers. For the first layer here is actually got from the flattening of the convolutional backbone, and the second layer, which is in pink color, it has actually 256 nodes, and for the first and the second layers, which are in green and pink, are using railways there acquisition function, and for the third layer actually has 8 nodes that actually represent the 8 Q, the Q values of 8 axons. Now, after this build, this modulating build, now the axon with the highest value, or the highest Q value, will actually be adopted, which in turn affects the trajectory of the curve of the path. Now, the next is the design of the reward function. If the size of the map becomes bigger and bigger, the DPN will not be able to convert easily. So that is the first problem. The second problem is if the agent is also rewarded at the end of the target, then the planning becomes very difficult. But also, multi-objective planning is a very big challenge. So these three must be tackled at once. And so an exhibit reward function is designed for the 3D multi-objective of finding task, and such a reward function can be effectively guided the DPN to learn from exploration, and so we can use the reward setting function, which is defined by equation 6, where the RD is the distance penalty, and RS is the slope penalty. Then RW is actually the hit wall penalty, and RT is the reward reaching after reaching the target. And the model of the distance penalty, which is RD, actually has two parts. The first one is RD1 and RD2, represented in the present series. Let's dig deeper into it. So where the RD1 is a global distance penalty and RD2 is a step distance penalty. Now RD1, which is the global distance penalty, heuristic penalties the action that leads the next current position too far away from the destination in the 2D aspect, or it is denoted as in equation 8, and where the D2 into P(n1) is on PD actually means that the two-dimensional distance between the next current position and the destination dB1, dB lower 1 is actually a function, is a factor penalty with an intensity, and it is given to be fitted. But only R lower D1 is not enough, because it neglects the terrain information, and the second part, RD2, is introduced to also compensate the penalty of you know of this, where the equation R now defines RD2, where the D into P lower n and the P lower n plus 1 is actually a step distance, meaning the three-dimensional aspect now, instead of from just 2D, in 3D, because we are going to use RD2. Yeah, so the D lower B2 is also a factor of the intensity, and it is set at 10. So the slope penalty is then defined as in equation 10, where the K is the intensity factor, and K2, I mean K is actually set at 5. It is easy to understand that the penalty is proportional to inner distance action. Now, what about the hit wall penalty, which is R lower W? For it is defined as in equation 11, where the B, this B is the upper bound, and the R lower WX and the R WY are actually corresponding penalties, the X and the Y axis, respectively. And the gamma denotes actually the penalty intensity, and it is set at 5. Then they are defined in the same way as in equation 12 and equation 13. In equation 12 and in equation 13, and the terms in it are defined also here. So that is how that is how we design the reward function. From the reward function, we can go and look at the imitation learning using the heuristic method. Since now the state space is extremely vast, as we looked at, initially we reduced it from 100 by 100 by 10, I mean, but by 3, into 30 by 30 by 3. But that's still big, so the GPN will find it very difficult to convert. So the reward setting method is then used. Here are the two ways of improving this performance. One is through the imitation learning, where a naive heuristic method is exploited to generate helpful experience for training the GPN. And then also the traditional improved methods like the experience replay buffer and the double QNet are also used. But remember, all these are additions onto our random exploration, which means our random exploration has been boosted using imitation learning, and then also the experience replay buffer and double QNet. So then the DPN will be able to select the action that is recommended by the heuristic method with a certain probability. But as the training continues further, this probability actually reduces in value, meaning it becomes smaller and smaller in value. Now going to the height parameters that have been set. The language has been set as that. Okay, we have set the following height parameters: the learning rate, the discount factor, the batch size, the batch number for training, maximum episodes, the maximum learning step per episode, the training interval, the initial probability of random action, the initial probability of heuristic action, the initial probability of the GPN action, and the image factor. All have been set. Those values are seen on the screen. Now, the result of the reward in the training actually shows very clearly, if you follow it, shows very clearly that convergence is a problem to the DQN method, which is why this research is being taken. So now the diagram, which is figure 3, actually shows the simulated path results for the three-dimensional M method, and then also the DRL. The DRL is our proposed model, and this is the previous one, which was performing also well. But we want to see which one will perform actually much more better now. From this green dot to that red dot. Now the green line shows the path simulated by the DRL, which is our proposal, and then the orange one, orange line, or the orange curve actually shows the path which was planned and simulated by the 3D M model or method, and from there we can see which one has performed better using the table 2, which is all the planning results of the experiment. So the method are the DRL or deep Q learning, or the deep reinforcement learning, and then we compare it with the 3D model, whereby in terms of the energy, in the first case, the DRL as simulation has shown smaller energy use, and the other one has a larger bigger energy use. But in terms of the distance, still the 3DM uh, 3DM has performed better in terms of distance coverage than the RRD. But also in the second case, similarly, the RDL got, spent smaller energy, but they covered a longer distance. And in the third case, it was able to perform better. It spent small energy compared to the the 3DM, but also covered shorter distance than the 3DM. And also in the fourth case, the same. So from here, we shall be able to make the following conclusion that the DRL method actually plans more globally than the 3D method, helping vehicles to save time and energy. And so in the implementation, we solve two technical problems, and the DQN is hard to be trained. The first problem is that DQN is hard to be trained in a huge policy space. So the original map was transformed linearly to a relatively lower resolution form without losing its terrain information, which also lessens the burden of exploration of the DQN. And then also the DQN finishes planning and the planned path will be transformed into the original map using a path enhanced method. And then the third one is the imitation learning method is also used. So that is the first position. The second is how to model the reward function. So through path planning task based on idea of reward function, it will solve. Those are the ones, and so those are the conclusions. And our next works are in three areas. One is to realize that once the DQN is trained, it can be used for any three-dimensional map it has never seen before. That is robustness, and to also study a new deep reinforcement learning method that converges more clean than the DQN. And the third one is to explore how DQN can be used to solve the other path planning problems. With all this in mind, I can say thank you for your attendance. This is where the work references, these are the work references, this is where we have gotten these works. Once again, thank you.